Welcome back. Uh, okay, just to summarize what we have been doing so far, we are looking at the sequential decision making problem in the full information setting, also called as online learning. And we said that when you have an expert who is infallible, which is what we are calling as guru, then you can get a algorithm which is zero regret, because the number of mistakes that the algorithm makes is the regret, and that is logarithm of the number of experts at most. When you divide it by t and let t go to infinity, that will go to 0, because the numerator is logarithm of t, which is independent of t. But if the experts are infallible, is not infallible, which means that they can make mistakes, then we have a negative result saying that no matter how hard you try, if the adversary is too powerful, then you cannot really come up with any sort of algorithm. To overcome that, we are saying that we will slightly reduce the power of the adversary and we will consider only oblivious adversaries. And by oblivious, these are adversaries who knows everything. The algorithm, you publish the algorithm, but does not know the outcome, and that is important, outcome of the random bits. Which means that the algorithm is allowed to toss coins. If the algorithm is allowed to toss coins, I mean, when I say algorithm, it can be any algorithm. And if the algorithm can toss coins, then we won't let the adversary know the outcome of these coins. It cannot decide based on whether the coin fell heads or tails, whether I made a decision, and then it cannot look at it and then say change the answer, and that is oblivious to that. That is the oblivious part of it in some sense. Oblivious means it does not have that information. So because we now have expanded, or rather we have figured out that deterministic algorithms are no use for this problem, we have to work with a randomized algorithm, which means that we have to now ask what is the right way to measure goodness of these algorithms. Earlier we said that regret was the right way to measure goodness of this algorithm. Still we have to care about regret, but because it's a randomized algorithm, the regret can depend on the random bits that the algorithm uses, the coins that the algorithm tosses. So what we will worry about is we will define the regret very similar to how we did earlier. Regret of an algorithm A after t rounds is earlier was sum of t equals 1 to t, indicator of in our new notation y hat t not equals yt, that is the algorithm makes a mistake. Earlier this was our regret, right? So minus min over k, sum over t is 1 to k, indicator of x t k not equals yt, right? So this is the mistake made by the kth expert, and then you are summing it up. But now because it's a randomized algorithm, this y hat t, which is the answer that the algorithm gives, is a random quantity, right? Because I might flip a coin to decide whether y hat t is 1 or y hat t is 0. That's what it means to say the algorithm is randomized, which means that I cannot kind of just, if I define the regret like this, the regret itself will become a random quantity, because y hat t is random. So y hat t can take different values depending on the coin toss, so the regret itself can take different values. So what we want to study is kind of average case behavior, which means that I will now look at the expected value of this quantity, right? So this expectation is, for now we will think of it as over randomization of the algorithm. The algorithm is random, so on an average the number of mistakes made by the algorithm, how does that compare with the mistakes made by the best expert in hindsight? When I say hindsight, I fix some t, stop my algorithm at capital T rounds, and then ask the number of mistakes on an average my algorithm makes versus the number of mistakes that the best possible expert makes after T rounds. So, and that is what I will care about. So is the new modified definition of regret clear? Is the expectation clear? Whenever I am saying expectation, there should be something random inside. Here the random quantity is y hat t. Potentially yt could also be random, which means what? What does it mean to say yt is random in this case? What is yt? What is yt? Yt is 0 or 1, but who decides yt? the adversary decides yt. When I say yt can also be random, potentially the adversary is also having a coin, the adversary tosses the coin to decide what yt is. If so, then this expectation will also be over the randomness of the adversary, but for now let us say we will not worry about that. We will say that the adversary will be like a deterministic adversary, we will only worry about randomness of the algorithm. Now question is, does this solve our problem? Of course we have reduced the power of the adversary. We want remember what we wanted was the following, right? So we want limit t goes to infinity, the regret of our algorithm divided by t, we want this value to be 0. The question is, can we achieve this? If I allow randomization and if I change my notion of regret to this expected case, now first of all, can we achieve this? If so, what algorithm achieves this? That is the question. Before going to the algorithm, let us first try to understand why is this even useful? What power are we getting here, right? So by randomization. Of course, we know that the adversary cannot look at our answer and then change the thing, but then still the adversary seems very powerful, right? So it knows the algorithm completely, right? So we have published the pseudocode, it can control the experts, those things are still there, just that your algorithm can flip coins. Why is it suddenly a power that why am I calling it like a superpower, right? So that randomization, what is it helping? Let's try to look at that a little bit more. So for that, let's look at, intuitively try to understand what power are we gaining by doing this. What are we measuring? We are measuring the expected value of t equals 1 to t, the indicator of y hat t not equals yt. This is the expected number of mistakes the algorithm makes after capital T rounds. This is what we are measuring as, and then we will measure it against the best expert and so on, but this is what the algorithm actually is, what we compute from the algorithm's answers. Now this is same as this expected value of indicator of y hat t not equals yt. Why is this true? Yeah, linearity of expectations. So it is not independent, so that is the power of expectations. It does not matter. In fact, y hat t is not independent of y hat t minus 1, right? Because you are deciding for the tth round based on whatever happened in the previous t minus 1 rounds. These are not independent at all. These random variables are not independent at all. Still, expectation is linear irrespective of whether the random variables are independent or not. So this is just linearity of expectation. When I say linearity, it means that it's a linear operator. Expected value of x plus y is expected value of x plus expected value of y. Doesn't matter how correlated x and y are, doesn't matter if they are independent or not. Fine. So now what random variable am I taking the expectation over in the tth round? It's the indicator whether I made a mistake or not. So now what is the expected value of an indicator random variable? Well, what values can this guy take? I either make a mistake or I don't make a mistake. Make a mistake, it's 1, otherwise it's 0. So the expected value of an indicator random variable is just its probability, right? So this is just the probability of this. I am sure you have seen, especially if you have attended the tutorial diligently, you would know this. Even otherwise, this is not hard to see. So this is what we are essentially measuring, right? So for our algorithm. Now let's see why is this a superpower in the following way. Now at round t, I have some randomized algorithm. Let's not fix the algorithm yet. Some algorithm which is deciding whether I have to invest or not invest by flipping some coin, and let's say that coin has some probability pt of showing up heads, of deciding to invest, right? That is pt is just the probability that my algorithm in the tth round decides to invest. We don't know what the algorithm is, some randomized algorithm, and we want to understand how good is this algorithm. So pt is the probability that y hat t equals 1. Yt is what nature tells us or the adversary tells us, that can be 0 or 1, it can be one of these values. Now I claim, or rather I define the loss of pt comma yt, L is, I am just calling it loss. I am defining a function which takes in the probability with which I will invest and the actual answer, and then it will measure this quantity pt minus yt, the absolute value. We will see why this is a useful quantity to measure. So, if yt equals 1, yt is actually what the nature is telling me, what adversary is telling me. If the adversary says the stock market went up, then yt is 1. If yt is 1, what is loss of pt comma yt? Well, if yt is 1, this guy is what? pt minus 1, because yt is 1. But pt minus 1's absolute value, pt is a probability, right? So, it is between 0 and 1. So, pt minus 1 is 1 minus, absolute value is just 1 minus pt, right? So, because pt is at most 1. So, this value is 1 minus pt, which is the probability of what? Huh? What is p dash? Yt cap is 0, right? So, this is because pt is yt hat is 1. So, this is just the probability that y hat t is 0. Is this argument clear? It is just algebra, nothing magical going on here. On the other hand, if yt is 0, if the adversary says 0, now what is L of pt comma yt? Well, it is absolute value of pt minus 0, which is simply the probability that y hat t is 1. So, now let us look at everything put together. We cannot look at it because its page is too big, but so what I am trying to measure in each round is the chance that my answer and the actual answer differs. Now, there are only two ways in which my answer and the other answer can differ. I say 1 and the others 0. I say 0 and the other says 1, right? So, which means that if yt is 1, then I want to measure the chance that y hat t is 0. What is the chance that I make a mistake? If yt is 0, then again what is the chance I make a mistake, which means that what is the chance I said 1. Which means what? In both the cases, what I am really measuring, if I have to measure the expected value of whether I make a mistake or not in the tth round, which is equal to the probability that I make a mistake or not, which is exactly just measuring probability of I am saying 1 when the actual answer is 0 or the probability that I am saying 0 when the actual answer is 1. In both the cases, what we have just seen is that you can think of this as this quantity, because this quantity we just argued is if the actual answer is 1, this is just the probability that I am saying 0, if the actual answer is 0, this is just the probability that it is 1. So, basically we are just measuring pt minus yt, absolute value of pt minus yt in each round, right. So, which means that I might as well write this guy as sum over t equals 1 to t absolute value of pt minus yt. Is this clear? Algebraically is this clear? We will see why this is a superpower in a minute, but algebraically is this clear? Any questions? Okay, so why is this a superpower? Earlier, when there was no randomization, I was measuring whether I was making a mistake or not, and that value is either 0 or 1. Now I am tossing coins, and then I want to measure the probability that I will make a mistake. And that probability is, we just saw, is just the absolute value of pt minus yt, where pt is some probability that the algorithm is maintaining in the tth round with which it will decide to invest. Which means if I am going to essentially measure only this, it is as good as saying earlier in the deterministic world I had only two choices in every round, either a 0 or a 1, either I invest or do not invest, and then I will be measured whether I make a mistake or not. Now I have the choice to maintain any pt, and pt is a value between 0 and 1. you can equivalently think of it as there is no randomization. I provide a PT in the tth round, which is some number between 0 and 1. It's a deterministic algorithm which provides a number between 0 and 1, and then nature says either 0 or 1, and I suffer the absolute value of PT minus YT. This is exactly equivalent to saying I am going to toss a coin and then I will compute the expected value of whether I make a mistake or not. That is what we are arguing, which means that my decision space has suddenly expanded from just being 0, 1 to 0 to 1. Now we are still looking at a deterministic world. I mean, you can equivalently think of it as a deterministic world where this randomization has essentially given me the superpower of expanding my decision space from just 0 or 1 to any number between 0 and 1. But then the adversary is still giving me only 0 or 1. So my power has increased, right? So that's the essential reason why randomization helps. Is that argument clear? I mean, it's intuitively at least, right? So basically what we are saying is that, you know, y, which is what the adversary gives, is 0 or 1, but y hat, well, not y hat, y hat is still 0 or 1, but then I can think of this as y prime, which is a value between 0 and 1. Right. So, and I am only suffering the difference between any number that I predict between 0 and 1 and either 0 or 1, right. So, earlier I had only two options, 0 or 1, which means that the adversary can look, am I saying 0, then it will just say 1, and then I will suffer this mistake of 1, or the other way around. Now, if I predict somewhere here, well, if the adversary can only make me suffer this much, it cannot make me suffer the entire 1. So, my power has essentially increased by randomization. Clear? Questions? Okay, good. So now this is not like a proof or anything. This is just to say that, we are more powerful now. You can either think of reducing the power of adversary to become an oblivious adversary, or we are still in the deterministic world and say that, I won't predict 0 or 1. I am allowed to predict anything between 0 and 1, and I will be measured as the absolute value of what I predict versus what the adversary gives. Both are equivalent. Okay. So now what is the algorithm? Okay, at the end of the day we need an algorithm to make money. So what is the algorithm? We know it's going to be a randomized algorithm. We know it's not weighted majority because that's a deterministic algorithm that the adversary will beat us over. What is the most natural randomized version of that you can think of? So you are maintaining some weights over experts at every round. You are increasing or decreasing weights based on whether they are making mistakes or not. So now you have to make a decision. I am giving you weights of everybody. How will you make a decision? Earlier you said that I will sum up everybody who says 1, sum up the weights of everybody who says 1, sum up the weights of everybody who says 0. Whichever weight is larger, I will make that decision. That was weighted majority. That's a deterministic way to resolve this. Now I need a randomized way to do this. How would I do this? What's the most natural way?
I toss coin for everyone.
With what? So everyone's weight is, remember, okay, so let's go back to that weighted majority algorithm itself, right? So this was the algorithm we put down. So this is the step which is the deterministic resolution of from weights to decision, which is what we want to change. Initially everybody gets a weight of 1. If you make a mistake, all I do is I reduce your weight by 1 multiplicatively by 1 minus epsilon, right? So that is still the same. Now here I can't use this. If I use this and publish it to the adversary will beat me hands down. So now I have to be careful here. What will I do? Yeah, correct. Yeah, randomly select, but how? You have these weights, but I mean I can toss a coin and then randomly select also, fair coin, but it has to somehow involve the weights, no? What would be the most natural thing to do? Let's say the sum of the weights of people who are saying yes is 10 and sum of the weights who are saying no is 20. Now how would you combine 10 and 20 into a probability of saying yes? Equally likely, fair coin. But why? But then why maintain weights if you are going to do that? So this is the question, right? So everybody on this side are saying yes, their sum of weights is 10. Everybody on this side is saying no, their sum of weights is 20. Earlier we would just say that 20 is greater than 10, so I will believe 20. Whatever 20 group says, I will just go with it. Now I don't want to do that. I want to believe them only proportional to the weight that they have, right? Which means that I have to toss a coin, but what is the probability with which this coin will say?
The fact that the probability of supporting people with more weights is same fraction as.
So tell me a number for this particular case, 10 and 20. What is the chance that I will go with the 20 group?
2 by 2.
How did you come up with that? That's what I'm asking. 2 by 3 is correct. Huh? Yeah, all of you know this. I'm just asking as maybe a silly question. Yeah, so this algorithm is what is called as randomized weighted majority. So I'm not going to write the whole algorithm, but it's the same algorithm except that that step that I have boxed there, which is the deterministic resolution of decision, now will become the following: predict y hat t equals 1 with probability sum over everybody who says 1 their weights in the ith round divided by just the sum over all weights. This is what you did to get 2 by 3, I believe, right? So 20 by 10 plus 20, which is exactly this, I equals 1 to d, all weights. In other words, if you want to think of this deterministically, I am exactly predicting this number, this, I am not predicting between 0 to 1, but then I am predicting this value, right? So this is a number between 0 and 1. I can think of it that way also. Or I can toss a coin with this probability. If the coin falls heads, then I will predict 1, otherwise I will predict 0. As simple as that, right? So once you know that need for randomness is a must, then this is the most natural thing to do. Questions? The algorithm clear? Everything remains same. We are not changing anything, we are just changing the way we are deciding based on the weights. Yeah. Any other questions? Okay. So now, question is this a good algorithm or am I still cheating? Because I have given you so many algorithms and all of them have not worked so far. Yeah. Okay, so this is a good algorithm. I won't have the time to prove this. It's not too hard actually to prove this, but in the interest of time, I'm not doing this. But you need to set your epsilon very carefully. If you remember, epsilon was the shaving away fraction, right? So how much weight should you decrease so that you kind of do this carefully. So if epsilon is set carefully, and I will tell you what carefully is in a bit, then the regret of RUM, which is nothing but randomized RWM, right? So RWM, randomized weighted majority, can be shown to be something like square root of t logarithm of t. Again, when I say belongs to, okay, so let me say less than or equal to some constant. Okay, this is also fine. Yeah, square root of t logarithm of t. Again, it needs some work to prove this, which I won't do. I'll kind of give you an intuition as to why this is the kind of a thing that you should expect. But what does this tell us? This tells us the following, right? So now, if I divide this regret by t, and I look at per round regret, so that would be, you know, square root of t logarithm of d divided by t, and that is square root of logarithm of t divided by t, and this goes to 0 as t goes to infinity, right. So, this is a no regret algorithm, right. So, as you play this game again and again, how much are you away from the best possible person in hindsight? Remember, the best possible expert can change over time, right. Suddenly after a point of time a different expert catches up and then he becomes better. This algorithm will still track that person. That is why you need that careful choice of epsilon. Again, for completeness sake, I will tell you what epsilon is. Again, this needs to come from analysis, otherwise it is very hard to give intuition for this. You have to choose epsilon as logarithm of d divided by t. If you choose it like this, then this holds. The regret of this particular algorithm is at most this. So, the main point here is that, you know, if forgetting how the analysis of this, what I am trying to argue is that whatever we thought was an intuitive algorithm, the weighted majority algorithm, if you just include randomization in the most natural way, then you can argue that that is a zero regret algorithm. Now, one might ask, well, this is going to 0 at a rate 1 by square root of t, right. So, the numerator is a constant, right. So, that depends on the number of friends you are asking for advice, that is square root of logarithm of t, that does not change with t, but then the regret itself goes down with as a rate of 1 by square root of t. Now, one might ask, well, is this the fastest algorithm, right. So, I want to catch up with the best guy. Now, this is saying the rate at which you will catch up with the best guy is 1 by square root of t. Now, is there a different algorithm which will catch up faster than this, right. So, which means that can we argue, like, is there a lower bound for this is called as learning with expert advice. Is there a lower bound for this? Maybe, for instance, maybe you can go at a rate of 1 by t itself, I do not know, right. So, for instance, in the case of stock market guru, we were actually going at the rate of 1 by t, because the number of mistakes was logarithm of d, and that was our regret, and then logarithm of d divided by t would go faster to 0 than square root of logarithm of t divided by square root of t. So, then the question is, is it that our algorithm is not capable of converging to the best possible expert in the fastest possible way, or the adversary is powerful enough that no matter what algorithm you use, it can make you suffer this much regret at least, right. So, the answer to that is not too hard, but I will just state what the answer is, right. So, in fact, randomized weighted majority is optimal. That is, no matter how hard you try to come up with a different algorithm, you will not be able to achieve a regret which is smaller than square root of logarithm of t. In other words, the adversary can make you suffer square root of logarithm of t no matter what you do. And what the way, I won't prove it, but then the way you can think of this is that the argument for that would be as follows. No matter what your algorithm says, the adversary will just flip a coin, an unbiased coin, and then will decide yt randomly, right. So, you do randomized weighted majority, you do whatever randomized algorithm, the adversary will decide on the outcome by just flipping a coin. Now, such an adversary can make any algorithm suffer at least square root of t, is a probabilistic fact that one can prove, which I won't do, which means that no matter how hard you try, you cannot get an algorithm which is better than, whose dependence on t is better than square root of t, right. So, in that sense, this is an optimal algorithm. There are other optimal algorithms, right. So, for instance, there is so this algorithm appeared in different avatars in all throughout the 90s and early 2000s. So, there is another algorithm which is popularly called as the hedge algorithm, and the word hedge itself should indicate some relation to stock markets, right. So, hedging is a popular financial term. Have you heard hedging? What does hedging mean to you? No? Okay, so basically don't place all your eggs in the same basket. That's what that proverb is, what hedging means, right? So if you have a bunch of stocks, then don't put all your money in the same stock because you are doomed for failure. So hedge just means that you spread out your money across different stocks. In this case, hedge your money across different experts. So maintain weights over experts, right? So that's why it's called hedge. I mean, the original idea was people thought that they might make money with this, and then they tried to come up with these algorithms. Of course, you can make money only at this rate if you use this algorithm. Still not a bad idea to try. Hedge, okay, hedge would do, only difference hedge would do is that Wt plus 1 of I is Wti, instead of 1 minus epsilon, which is what we were doing to reduce the weight, it would reduce it as something like e to the minus eta times the loss, right. So basically you can think of it as e to the minus eta, if in this particular case. But that's just a matter of convenience, because you can prove a few other things if you are looking at e to the minus eta. Anyway, e to the minus eta is less than or equal to 1 minus eta for small enough eta, so these two things are almost the same. That's just for historical context I am giving them. Okay, any questions? So is this overall idea clear? This algorithm is super simple. At the end of the day, all the algorithm that I am suggesting is maintain weights, flip coin based on proportional to weights. Now, to prove that this algorithm is a good algorithm is what the whole game is about, right? So, and then in what sense? So here is a precise sense in which this algorithm is a good algorithm, which is the sense of regret. Okay. So now what we are going to do is kind of push this a little bit more, try to view this in a slightly different way, so that I can make a connection to machine learning, right. So because I mean all this looks like stock market analysis, and then I'm trying to make some money and so on, but where is the machine learning part here, right. So we'll try to kind of connect it to machine learning in a slightly different way. Again, I will try to do this, I won't do this extensively in the interest of time, but then I will at least hint and then tell you where to look for to need more details. Here is a slightly different way to think of this. This is a different protocol for t equals 1 to t. It's a different online learning game, so to say, right. Now, in the previous game, at the beginning of the day, all the experts are giving us some advice, and then the algorithm makes a decision and then receives a feedback. In this game, what the algorithm does is, the first step is the algorithm's move. The algorithm chooses, I will tell you what this is, some vector in a simplex. We will come to this in a minute. The algorithm makes the first move, it chooses something, and now what the algorithm receives is a loss vector, which is, let us say, some d-dimensional vector of positive numbers, d positive numbers. For example, if d is 3, this can be 1, 2, 3, for example, right. So which means it's a loss vector in 3 dimension. This. What the algorithm suffers, right. So after it makes this choice, the algorithm has to suffer something. The algorithm suffers the dot product between what the algorithm chose and what the algorithm received, which is the dot product. I am sure all of you must have seen this, is just the sum of the component wise product. All of you know dot product. Okay, thanks. That's it. So this is the protocol. So the algorithm chooses something, and this is what is called as a simplex. So what's a simplex? Yeah. Why are people saying something and then when I turn I don't get it? It's okay if it is wrong. What was that? What is a simplex? Anybody knows what a simplex is? Okay, fine. The simplex is just a set of vectors. Everybody knows what a vector is, right? So a vector is like a bunch of ordered numbers which has a direction and a magnitude. So in 2 dimension, the simplex is just this set. How would you describe this set? What is special about this set? When I say this set, every point in this blue line, this is what I am calling as a simplex in 2 dimension. What property does every point on this line satisfy? Distance from 0 is less than 1, but then that is not special to this set only, right. So, I cannot describe this set or define this set like that, because for example a point here also has distance from 0 less than 1. Yeah, value between 0 and 1 in both coordinates, but then here is also a point which is value between 0.
We can generate the whole line segment by linear combination of both the points by taking the coefficient between 0 to 1.
That's true, but that's true for any point in the in R2, no. So if you take the linear combination of 1 0 and 0 1, you might get any point in R2. Not, I'm saying what characterizes this set.
If we take a coefficient between 0 to 1, then we can generate the whole line.
Okay. So if you take the coefficient between 0 to 1, no, but if you take coefficients, let's say 0.5 for the first one and 0.2 for the second one, I will get this point also. The coefficient should have some property, right? Or rather, what property does every point? Yeah, their summation should be 1. Basically, every point on the blue line are between 0 and 1 and they sum to 1, right. So, this is the set of all vectors in 2 dimension such that x1 is greater than or equal to 0, x2 is greater than or equal to 0, x1 plus x2 is 1. That is the simplex. Yeah. So, this is the only set of points that has this property. So, now why is this an interesting set? Well, you can either think of this as a set in 2 dimension, or you can think of these as probabilities over 2 items, right. All ways of assigning probabilities over 2 items. So, that's the interesting parts, and we will see why that is useful. So, in 3 dimension, where would this set, how would this set look like? Okay, my straight lines are curvy, but where is this set in 3 dimension? Give me some points in this set in 3 dimension.
Region between all the
1 1 1 is not in this set.
like 1 1 like y1 and the rest to 0.
Okay.
X1 the rest to
1 0 0, 1 0 1 0, 0 0 1. These 3 are there, and then anybody, you can join these lines, and then this is the region in 3 dimensional simplex, right. So basically what we are saying in this particular problem, and then we will connect it to the stock market problem in a bit, is the following. What we have is this is called as a linear game on a simplex. So what is happening here is that at every round the algorithm is given this whole simplex. It has to pick some point from this simplex. It is a d-dimensional simplex. In 2 dimension means this is the line from which it has to pick something. In 3 dimension means this is the region from which it has to pick something. D dimension, I mean, there is a equivalent object. Now the algorithm makes that choice at the first moment, and then it receives a loss vector, right. So it kind of receives a loss vector, and then what it suffers is the dot product between what it chose and what the loss vector that it received. That is the amount that the algorithm suffers in that particular round. Now, of course, what you care about in this case is the regret. Let us say again, let us say the goal is to minimize regret, and then we will see how this naturally connects to the previous problem. T equals 1 to T Pt comma Lt, this is the dot product that the algorithm suffers, minus, now what am I regretting over? I am regretting over the fact that if I had picked the same point for all T rounds in simplex, I would have suffered a certain amount of loss, right. So, every point gives me a certain amount of loss. I could have picked a single point and then I would have suffered, let us say if I pick a specific P, I want to minimize over all P in the simplex, sum over T equals 1 to T P transpose Lt. If I had picked a single P and stuck to it for all T rounds, then every round I would have suffered P transpose L1. Okay, the notation, let me be careful, P comma Lt, it is the same thing, sometimes it is called transpose also. P comma L1, P transpose L2, dot product of P with L3 and so on and so forth, and then I would have suffered the sum of this. But my algorithm chooses P1, P2, P3 in different ways at every round. So, I want to look at the regret of the algorithm as how much algorithm suffers minus how much I would have suffered had I picked the best P. The same definition, right. So, just that now earlier we were playing with against a set of experts, now we are playing against a set of points in a set. Is the definition clear? Any questions here? Okay. Now I am saying, first thing to say is that where can this minimum occur? We do not know how LTs are. LT is what the adversary is giving us, right. So, L1, L2 till LT is what the adversary has given us, but can this occur, let us say we are in 2 dimension again. Can at the end of T rounds, I have seen L1 till LT, all of them are 2 dimensional vectors. Can this point be the best possible point? How would you think about this? So, let's quickly think of an example. Let us say T is 3. Let us say T is 3, first round I got 1 2, second round I got 3 4, third round I got 1 3. Now, which is the point P, right. So, P is, I want to choose P from this set of points. Where is the P such that P comma 1 2 plus P comma 3 4 plus P comma 1 3 is as small as possible. Well, what is this? I can write P itself as P1 P2, some point here, arbitrary point as P1 P2. Now, what I am asking then for is P1 into 1 plus P2 into 2, that is this value. This becomes P1 into 3 plus P2 into 4, and this guy becomes P1 into 1 plus P2 into 3, which is basically P1 into 1 plus 3 plus 1, this plus this plus this, plus P2 into 2 plus 4 plus 3, which is P1 into 5 plus P2 into 9. P1 is 1 and P2 is 0 is what he is saying will give us the smallest. Why not anything else? Both will start contributing, right. So, basically all we are saying is that I am adding up the first component, adding up the second component, and then there is one component which is smaller, the other component which is larger. Now, I need to put my weights on these two components, I need to take a weighted sum. Now, I want to minimize the weighted sum as much as possible. So, I might as well put all my weight on the smallest component, right. So, because the moment I put something on a larger component, I am going to suffer only more, right. So, is this specific for this particular example, or this is true in general? This is true in general, right. So, which means that though I have written my regret in this case like this, it's basically the answer is going to be one of the endpoints of this simplex. There are only d endpoints, right? So in the 2-dimensional case, it has to be either 1 0 or 0 1. 3-dimensional case, it will be 1 0 0, 0 1 0 or 0 0 1. Similarly, in the d-dimensional case, right? So which means that let's call that E1 till ED, and then I can say this is EI or EK, right? So it has to be one of the endpoints. So basically, then what I am saying is that I am playing a point from the simplex. My algorithm can play different points from the simplex in different rounds, and I am comparing myself against one of the endpoints. Now we are beginning to see the connection between what this problem is doing and what we were doing earlier. In the stock market case, all the experts were giving us some answers, and then I made a decision to, based on some probabilistic algorithm, I made a decision, and then I received a feedback. Now what we can do is that I can abstract out this problem and say that, you know, I am going to say that the adversary is not giving me whether the stock market went up or went down. Instead, because the adversary has the power to decide what the experts are saying, the adversary would just tell me whether each expert was correct or not. It will give me a vector, loss vector in d dimension, which will tell me how much loss does each of the experts suffer. In the stock market case, it's either 1 or 0. The adversary will combine these two parts, right? So the actual answer and what the expert are saying, because these two are being separate is not really useful for us. What is really useful for us is that what loss does each expert suffer. That's all we care about, right? Let's say the adversary in an adversarial way generates that loss vector. What the algorithm picks is just a distribution over these fixed experts, which are like fixed endpoints, right? So and now you want to learn which is the best way to combine these fixed endpoints so that this adversarial loss can be as small as possible. I mean, you can beat the adversary, right? So basically the loss vector is, you know, you can think of in the expert setting, you can think of this as, you know, this is indicator of yt equal to xt1, indicator of yt equal to xt2, and so on, indicator of yt equal to xtd. The adversary gives me, I initially decide, I mean, all experts are equally good. So my initial PT would be just 1 by d, 1 by d, 1 by d over the simplex, and now the adversary gives me a loss vector which is telling me whether each of the expert was correct or not, right? So and now I will adjust my probability vector, right? So basically in this case, let's say if in the 3-dimensional case, now I am playing a point from the simplex, oops. I'm playing a point from the simplex. Let's say initially I will play this point. Now because the adversary is saying the loss for each of the experts, maybe this points, these are the 3 points which really matter, right? Now what will happen is, over time, if this guy is the best guy, my probability distribution will slowly converge to this guy, which is exactly equivalent to what we were doing in our randomized weighted majority, right? Now the advantage of doing it this way is that, you know, this loss need not be a 0-1 loss, it can be an arbitrary loss vector, right? So you can generalize this problem from the stock market to a much more broader class of problems, saying that, you know, I pick some model in a machine learning sense. Let's say the model in this case is constrained to be in the simplex, and then some loss comes to me, and then what I want to measure is, you know, had I gotten all these loss vectors together, which is the best model that would minimize the loss in an offline case, as if I had done an offline standard machine learning problem. But now here I am doing an online version. How close is the online version to the offline version, right? So basically that's the connection. Of course, for example, just to give you a specific problem, now you can have a protocol where, you know, for example, for t equals 1 to t, you can so now you can predict some WT, a d-dimensional vector. Let's say now you want to do online classification, right? So now I'm kind of saying that the same ideas can generalize to online classification. Let's say at every round I decide that I'm going to make a decision based on some WT, which is a vector in d dimension. Now I will receive a loss vector, right? So in this case, the loss vector, earlier, you think of it this way, right? So basically, instead of loss vector, I will receive a loss function, which is some function which maps RD to R, and now I suffer f of WT. This is the machine learning connection. So what I will want to regret would be sum over t equals 1 to t f of WT minus minimum over W in RD sum over t equals 1 to t f of W, right. So now you can think of this f of W, think of this as the following: there is some data point that comes in, the adversary does not tell me what the data point is, I am telling what the model WT using which I am going to classify this data point. The adversary will tell me, what is the loss that I suffer for this particular data point, right. So this could be, for example, WT transpose XT minus YT square in the case of a regression problem, for example, right. So this is, the adversary just tells me that f of W, f is just, f of W is just W transpose XT minus YT square in the tth round. So this is a function that the adversary is giving me, and now for the WT that I have, I will suffer the squared loss between what my prediction, my WT predicts for the XT YT, and and what I want to do is that over time I would have gotten t different data points, and now if I had all the data points given to me together, then I would have simply run a regression problem which would have been to minimize t equals 1 to t, minimize over W transpose XT minus YT square. This is what my standard regression problem is. But now I cannot do this because I get the XT one at a time, right. So which means that what I am actually suffering is t equals 1 to t WT transpose XT minus YT squared, and now I want to compare it with, had I had all the data points together, I would have done a standard linear regression and I would have suffered certain amount of loss. How much is my online algorithm comparing with the best possible offline algorithm, offline machine learning algorithm, right. So I want to compare this with minimize over W, sum over t equals 1 to t W transpose XT minus YT square. So this is the best possible offline algorithm. This is the offline machine learning algorithm's loss. This is the online loss. And now we ask the question, well, can I be as competitive as the offline algorithm, right. So do I need to see all data at once to minimize the loss to a certain extent, or can I do this in an online fashion and be competitive in the regret sense, right. So that would be the machine learning connection. Any questions here? I mean, this needs a the algorithms is not going to be the previous algorithm that we saw, because that was working only for a probability space. This would need a slightly different algorithm which we won't discuss here, but this is the same type of connection that you would do to the for the ML case. Is the idea of regret naturally extending to loss functions and machine learning problems clear? That's the main thing that I want you to take away here. Okay, cool. So what we would do next quickly is to look at multi-armed bandits, which is the second problem that I spoke about in the morning, right. So let's say part 2 is coming later than what I thought, but this is the partial information setting. We'll just look at one algorithm in the interest of time for this. What is the setting here? If you remember, this is the medical diagnostic setting. You have a bunch of options to take. You take an option, you only receive feedback for the choice that you made. You don't know about how things would have happened had you decided a different thing, right. So sometimes this is called as the multi-armed bandits setup. One of the reasons is because you can think of, if you have seen, I don't know, yeah. So if you had ever gone to Las Vegas or some gambling, even I think there's something in Goa as well, right? So if you had ever gone there and pulled a slot machine, right? So there would be a machine. You put money, you pull it. Rarely, you you kind of get a reward. You get lucky, and then you get more money. Most of the times, you will be losing money, right? So, but people still, people believe in luck more than that they should, and so they put money and then kind of lose money, right? So that's what is called as a arm slot machine, a slot arm. And then, especially if you go to Las Vegas, you will see like old people who have all their life savings. They don't have, perhaps their kids have left them, they don't know what to do with their lives. They'll just go to Las Vegas, put money, pull the slot, put money, pull the slot. They'll be doing this the whole day. I've seen people doing this the whole day. So why is it called a bandit? Because the machine is rigged, right? So it's there to game, and the system is completely gamed, right? So you will never win in expectation. You might win occasionally, which is what will keep the game going, but then in expectation this club will always win, and that's even made public there, right? So you know that you are going to lose in expectation, still people think that no, I am a lucky person, and then go and lose money, right? So now this is a version of that, where instead of one slot machine, now you have multiple slot machines. Every time you pull a slot machine, you get a reward. This reward could potentially be generated by an adversary, or could be somebody is tossing a coin and deciding whether you get a reward or not. Now let's say if there is a coin sitting behind each of this, let's say each coin has some bias associated with it of giving a reward. Now every time you pull an arm, somebody tosses that coin. If it falls heads, you get a reward. If it falls tails, you don't get a reward. Now your goal is to identify that arm, in this case this one, that will give you the highest reward, because if you have that, then you can keep pulling that arm so that you get as much reward as possible, right? So but then this is a case where the rewards are generated in a stochastic fashion, but what we will see today is where the rewards, we are in a bad mood, so we will see the case where there is an adversary sitting and creating problems. So what is the practical application of it? One is the medical diagnostic thing that I said, where you can think of these arms as possible tablets, and then you pulling an arm is equivalent to prescribing one tablet, and then the reward is what you get, which could be adversarial or probabilistically generated. Another example could be an user walks into your to Amazon, and then Amazon has to, or Netflix or whatever, and then they have to show ads. They have 10 different potential ads that can be shown. Now these can be thought of as arms. Now you show one particular ad. Now the user clicks the ad or does not click the ad. So what you know is whether this ad worked or not, but you don't know whether if I had shown a different ad, would the user purchase that product or not. You don't know that. So it's still a partial information setup in this case as well, right? So there are several such possible examples. So let's see how we can develop algorithms here. Is it an easy problem or a harder problem than online learning? It will be harder. Why? We have only partial information, clearly, right? So let's say the player or algorithm chooses an arm, some arm IT from a bunch of arms that it can pick, right? So these are arms or actions, depending on how you want to call it. Suffer or observe some loss, LT IT in 0 1. That is, there is a loss vector. Every arm has a loss. You don't just get to see that, right? So you only get to observe the loss that you prescribe, you for the arm that you chose, right? So this is the protocol. Now what we will assume is so is the protocol clear? I mean, is the notation clear? So basically I am picking an index which corresponds to one of the D arms, and then if there is a loss vector, I am only observing the IT index of this loss vector. I don't observe anything else, right? So only for the IT that I choose, I observe that loss. Of course, the loss vector can be different in different rounds. That's why there is a T dependence on the loss vector itself. Okay, so we'll assume again a deterministic but an oblivious adversary. So the adversary chooses losses before the game begins. Let's say we assume that. Again, the adversary can look at your algorithm, everything is possible, but because the adversary cannot look at your specific answer and decide anyway, so we can kind of assume that the adversary is choosing like an infinitely long matrix. So let's say there are d arms and t equals 1, t equals 2, dot 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 dot. It keeps on going. In the first round, maybe it chooses 0, 0.2, 0.3, 0.5. In the second row, it chooses 0.5, 0.3. I mean, it can decide this before the algorithm begins operation, but it can look at the algorithm and then it decides this infinite sequence matrix, let's say. Now, if you pick the second arm in the first round, you only get to observe 0.2. You don't know anything else about this vector. If you pick the fourth arm in the second round, you only observe 0.5. You don't know anything else about this other vector. But we have to assume that there is this vector so that we can meaningfully talk about regret, right. So the way you will again define regret is exactly the same way. Regret is expected value of sum of t equals 1 to t LT IT minus minimum, let us say in this case you have only d arms, which arm would give me the best value, because there is this entire matrix. Now there is one arm which would have given me the smallest error after t rounds, and I want to compare myself with this. It is an expectation because again, you know, if it's a deterministic algorithm, even in the full information setting you are not able to do anything. In the partial information it's only getting harder, so you have to have a randomized algorithm, that's clear. So this is random choice, randomness over the algorithm. Okay, what should we do? So is the setup clear? Any questions about the setup, or how is it differing from? Nothing is majorly changing except what you are observing. We cannot do weighted majority or randomized weighted majority. Why? We cannot eliminate. Well, we cannot, because we don't have the loss vector, right? So if you had the loss vector, then you could have done something, but you don't have the loss vector. So you only observe one component of this loss vector. That's the problem. So we still want a randomized algorithm, right? So that is clear. So let me put the bare bones out there, and then we can brainstorm on what to do, right? So t equals 1 to t, what I would do is my algorithm has to pick my arm to pull, or the experts to or the tablet to prescribe in a probabilistic way, which means that there is some probability over the possible actions, which means that this is a point in the simplex that it is picking in a probabilistic fashion, right. Earlier, once it picked in the linear game on the simplex also, it was picking something in a random way from a simplex, but then it got the entire loss vector as output from the adversary. But now it doesn't get the entire loss vector, it only observes play IT and observe LTIT 0, question is how do we do this, right? So how to do this step? This is the easier step. This is the only step that that will determine this algorithm. What would you do? Let's discuss. Any thoughts? Yeah. So you are comparing against that action or that arm which gets the least loss over t rounds. Now you need a strategy to figure out which is the good one. What can we do? Any thoughts, any ideas that come to your mind? Yeah, that's the problem. That's true. But what can you do to mitigate that problem? Each step we try. But okay. But we don't know LT. So the problem. Okay, the earlier thing is that at least you could have computed this if you know LT completely. Here you are not even shown LT, right? So you can. Yeah, if you choose that randomly, then what is the guarantee that you would do well with respect to this guy, right? So if you are choosing it randomly, then it's going to be 1 over d probability for each of the actions. But now the adversary can make sure that, you know, on an average you are suffering much more, but then there is one guy who is very good, but then you would have picked him only with probability 1 over d, right? So that is not going to work, no? What else can we do? Any thoughts? Yeah, so correct. So it has to be, that is a good point, and that's a correct point, that the probability with which an arm is picked should somehow depend on how well this arm has been doing or not. In fact, that's exactly what we did in the standard weighted majority case as well, right? So the arms which are doing well, arms were experts there, experts which are doing well, we picked them with higher probability, doing low, we are picking them with lower probability, same thing. But here you don't have this loss to be computed at all for the other guys, that's the problem. So let me give you a potential algorithm and then ask you what you feel about it, right? I have D people or D arms. First 100 rounds I will just use the first guy. Next 100 rounds I will just use the second guy. And then if I have 10 people, then I will do 1000 rounds. At the end of 1000 rounds, now I have some loss that I have observed for each of these people. Now I will use this loss somehow, let us say in a simplistic way, I will pick the one with the least loss and then I will just use that person from there on. Is the idea clear? So I will allocate 1000 rounds where I am just collecting information. First 100 rounds first guy, second 100 rounds second guy, and then 900 to 1000 the 10th guy. Now everybody, for each I know, I observe only that person's loss or that tablet's loss if there are 10 tablets, right? I will give it to 100 people, I mean let them die or not, I don't care, but I will just give it to 100 people and then observe how the tablet is performing. And then I will do this for 1000 rounds. I know some values for each of the tablets, and whichever tablet was doing the best, I will start giving that to everybody from there on. Is this a good idea or a bad idea?
In the adversary, we had this matrix, right? So if we have like first 100 rounds, we take say R1, and for second 100 round, will we be considering T is equal to 100?
What equal to 100? T equals 101. Correct.
And that corresponding to that vector or
that vector. So basically when I say first 100 rounds I am going to use the first arm, the adversary will show me these things. After that the adversary will show me these things and then these things and so on. Is this, what I am asking is that after this I will see which one gave me the smallest loss and then I will use that from there on. Does this sound like a good algorithm, or are you seeing some issues with this? If you are an adversary, can you beat me in this algorithm? How would you beat me?
we know that because the adversary knows the loss amount,
Hmm.
and he'll definitely know which one will give the least, and he can straight manipulate that.
Yeah. Precisely, right. So after 1000 rounds, the adversary knows that you are going to pick the one with the smallest anyway. Now for the first 1000 rounds, it will make sure that one tablet is actually doing very well. from the 1001st round onwards, that tablet is going to kill everybody, right? So, but because you have only looked at 1000 rounds to figure out which is the best tablet, now from then on you will actually be choosing the wrong guy. So that's clearly not going to work.
We randomize the choice of, instead of sequentially doing any order, we can randomize the.
Yeah, randomize is important, but randomize where is the question, right? So the rounds that we consider for each among the 1000, that doesn't matter. Okay, so you're saying I will randomize in each round, I will randomly, yeah, but how does that randomization has to be specified, right? And then we can ask if the adversary can beat that or not. So if you are, I mean, uniformly at random picking one guy, then the adversary will beat you easily, right? So one fundamental problem here is the following, right? So I have some information that I have collected so far, and then I can exploit that information, saying that the arm that is performing well so far will continue to perform so well from now on, but that's not enough, right? So because some other arm might actually become better after that, right? So I also have to keep exploring. I cannot like kind of miss other arms, right? So there is this exploration versus exploitation dilemma that one suffers in this case, right? So what I am going to now give you is it's a very smart algorithm, and I'll, in the interest of time, I'll give you the algorithm and then we'll make some comments about that. So this algorithm goes as follows. This algorithm maintains weights over experts, as our randomized weighted majority would start, right? So it will do for t equals 1 to t. At every round, it decides on a probability vector where, you know, pt of I, the probability of choosing the ith arm is just the I mean, you just normalize these weights, right? So basically you maintain weights and then you divide the weight of a person by the sum of the weights, so that's the normalized weights for pt. Now what I will do is I will draw according to these probabilities and I will observe LTIT, and let us say that is between 0 and 1, some loss value. It need not be 0 and 1, but let us say it is between 0 and 1, right. So far all I am saying is that I am maintaining some weights and then I will pick an arm proportional to the weight with respect to the other weights of arms, and then I am only observing that person. Now here is the most interesting part of this algorithm. Now why can't I do randomized weighted majority here? Because I am not observing the entire loss vector. I only observe one single value, and that is the key problem here. The way we are going to fix this is that we are going to construct a fake loss vector, which is as follows, right? So construct a fake, okay, fake within quotes, because that is something that I am saying, not in the literature, loss vector LT in 0 1, or rather in RD. I am going to somehow create this fake vector, and now once this fake vector is there, what I will do is I will pass this to my randomized weighted majority algorithm and use this fake vector to update my weights. And the way I would do this is as follows, right? So Wt plus 1i is Wi into, so earlier we were using 0 1 losses, either, you know, my expert was correct or wrong. Now the loss could be any value number. So you can, earlier I would use e to the minus eta or 1 minus epsilon, both are equivalent. Now I will do into LTI, right? So if the loss is large, then I am pulling down the weight larger, right? So this is, I mean, you can think of this as equivalent to Wi into 1 minus epsilon times LTI. Earlier in the expert setting, LTI was either 0 or 1, so this was either I leave the weight as such, or I would multiply it by 1 minus epsilon. Here the loss could be any number. We are just generalizing that. So this is not a very special thing here. So this is how I update the weights. Now that's it. This is the algorithm. Just that I have left out the most interesting part of the algorithm yet, which I will come to, the red part. So all I am saying is that I will somehow use what I already know for hedge or randomized weighted majority type of algorithm and then use it here. The only thing that I could not, bottleneck for not using that was I did not have this whole loss vector. What I am saying is that I will construct a fake loss vector. The question is, how do I create this fake loss vector? That's the only thing that I need to create, right? So this is not in fact LT, let's call this L hat T, because this is, I don't know if it is the actual value, right? So this will be some approximation, and I don't know the exact LT because I am not observing the LT which the adversary has chosen. So how should I do this? So what property do we think we want of L hat T? Of course, if it is equal to LT, that's the best thing, but we cannot achieve that because the adversary is not showing us the actual value. But we are only seeing one number, that's the problem. No? So we are just seeing one number, but then we want to convert it into a vector. We are seeing one number which is the loss for the arm that I picked, but then what I am trying to do is that from that number I am trying to construct a whole vector, which is the more smartest part of this algorithm, and that's why this took like 60-70 years for somebody to come up with this algorithm, since the problem was actually posed. But it's not actually too complicated if you think about it in hindsight. What you want to do is that you somehow want this L hat T that you are creating to be an estimator for the LT that the adversary actually has in his hand, but not showing you. The adversary is only showing one element. I will just take another 5 minutes and close. The adversary is taking only one element, but then you want your L hat T to estimate that well, and it seems almost impossible to do this because you are only looking at one value. How can we estimate a whole vector by just looking at one value? And here is the trick, right? So you are going to construct what is called as an importance weighted estimator. This is perhaps the takeaway from this second part of the lecture. You will construct L hat T as follows. L hat T would be this vector. Now let us say I have chose this is my IT, right, the arm that I chose. Now for every other arm I will just in a dumb fashion put 0 as the value. For the arm that I chose, I observed LTIT, the correct value for LTIT, that I have observed, but I am not going to use that. What I am going to do is that I am going to divide that by the probability with which I actually picked that arm in this round. That is the trick. Now that sounds, why would I even do this? What is happening here, right? So let us say there are 10 arms, or rather 3 arms. To simplify things, let us say there are 3 arms, and now I had a probability of 0.1 of picking the first arm, 0.7 of the second arm, and 0.2 of the third arm. This is the probability with which I picked an arm in this round. Now let us say the true loss vector was 10, 20, 30. Now if I pick the first arm, then what is the L hat T that I am constructing? What is the L hat T that I am constructing? If I pick the first arm, well, if I pick the first arm, I observe 10, I do not observe the other ones, so the others are 0. I observe 10, but then I divide 10 by 0.1. If I pick the second arm, if first arm, if second arm, then L hat T would be what? 0, 20 by 0.70, and if third, then L hat T would be 0, 0 30 by 0.2. Now I only have 3 possible answers that I could have got, right? So for my fake loss vector, it's either this or this or this, but this happens with probability 0.1, this happens with probability 0.7, this happens with probability 0.2, because that's how I picked this up, right? So which means in expectation, what is L hat t? Well, with probability 0.1, I send this guy, with probability 0.7, I send this guy, with probability 0.2, I send this guy, which is what? What is the answer to this? We get L 10, 20, 30, right? So which means what, this is what is called as what type of an estimator from all your statistics tutorials. This is an unbiased estimator, right? So though I don't know what the vector is, right? So what I have managed to do is I have created an unbiased estimator for the true loss, and that is actually good enough, right? So for now it's all, you can do this analysis because you are not actually giving the true answer to randomized weighted majority, but then you are giving an estimate which is an unbiased estimator to randomized weighted majority, and that is actually good enough to prove that this is a good algorithm. Any questions here? Yeah, so it keeps changing in the standard way that we have here. The weights increase, that will change the probability, and then from that probability I will pick this, right. So if I had observed LT completely, this is the previous algorithm exactly. Now because I don't observe LT completely, now I can be smart and create an estimator for LT, carefully chosen estimator. So which means that I will suffer something more. Now why is this, I will finish with one comment as to why is this actually balancing the explore exploit dilemma well. Well, I picked certain arm, I picked a particular arm, and then I am saying the actual loss that I observed, let us say I picked the first arm, the actual loss that I observed is 10. But now what I am saying is that I am pretending that the actual loss is 10 divided by 0.1, which is 100, whereas for the other guys I am saying the loss is 0, because the others weights will not change now, right. So their weights will stay the same, but my weight is going to go down a lot, right. So go down much more than what I actually observed as a loss, which means that if I am a good arm and I have to be played again and again, then that will only happen if the loss is also small and the chance with which I am picking it is high, right. So if the loss is small, the numerator will be small, the chance with which I am picking it high is large will also mean that the ratio is small. Only then my weight will go down a less, but even then my weight will go down. If I pick an arm, the weight of that arm will necessarily go down. For the other arms, the weight doesn't go down, which means that I am forced to explore the other arms also, right. So because the other arms relative weight increases with respect to what my weight is, right. So their weights will kind of catch up, and so I will eventually pick up the other arms also, right. So this is a subtle exploration exploitation dilemma that is balanced in a beautiful way in this algorithm. This algorithm is called as EXP3. EXP3 because there are 3 EXP words in this algorithm. One is explore, one is exploit, and one is exponentiation, which is just how you update the weights. So this is due to somebody called Peter Orr. I think if I got the spelling right, I think in 2002. This is like a seminal paper which described this algorithm first, right. So it's called the EXP3 algorithm. And let me finally finish with what is the guarantee for this algorithm. This can be shown to have a guarantee of square root of t d log d, the regret in expectation, which means that this is a zero regret algorithm, right. So you have to count for because if you have bunch of arms, like earlier you cannot kind of ignore certain arms, right. So you have to pay the price for exploration, and because you have only an unbiased estimator and so on, and that's why this d comes in. So you cannot like kind of get away with the logarithm of d like how we did earlier. Again, this comes from the analysis, but just for your information, right. So this is still a zero regret algorithm. Okay, so I'll summarize what we did today from the beginning, and then we'll call it a day. So we started looking at sequential decision making. There are three different types: online learning, bandits, and reinforcement learning. Full information, partial information with state change. What I focused on are full information and the partial information case. We just touched the tip of the iceberg. I mean, as all, I'm sure all the faculty in the summer school would have said that, right? So because like this is a whole course that I have kind of crammed into two lectures. There is one more course that will get crammed into the next two lectures by Chandru, but nevertheless it's a good idea to get exposed to these things. Now you know where to go and look for these things, right? So these are like the fundamental ideas in this. We looked at online learning, we looked at randomized weighted majority, showed that, you know, not show, but then argued that it's a optimal regret algorithm. You can use similar ideas to run online machine learning algorithms. I again touched upon that. In the bandits case, you can again use similar algorithms to smartly come up with zero regret algorithms. Okay, thanks, and I'll stop here. If there are questions, I can take them. Otherwise, we can